Thank you for coming. Welcome to Splice Machine. All right, let's make sure I've got this sorted. All right, cool. All right, so people always ask me, all right, Splice Machine, how did this thing come into being? And I'm one of the rare people. Most people talk at like a big data meetup and they talk about their success with big data. I'm not like that. I actually had a lot of failures. About 5 or 6 years ago, I really couldn't understand how a file system, Hadoop, could actually solve the problems that businesses were trying to solve. It was a file system, and they were viewing it conceptually as a database. I have tons of data. I want to throw it in there and organize it, run analytics, run applications against it, and all I could say to those people were, well, it's a file system. I can't, there's no concurrency models. There's no understanding of how to interact with data. You can't run a marketing, for example, application against this data. So I really struggled with Hadoop, and that multiple times. And from my perspective, I came up with the belief that, yes, there is a distributed computing movement going on, and the commoditization of data and that cost is critical, but you still need the capabilities of a relational database. That core data management is absolutely critical. So when I talk about Splice Machine, we're really about enabling applications by using our database, whether it's existing package applications or applications you're writing, to use our database to run, whether it's life sciences applications. Most of our initial use cases are in digital marketing because they're early adopters. So people running Unica, those type of campaign management systems that people have at scale. So that's really what we are. We're a relational database. Now this talk is about Spark, and I'm going to kind of go through what we tried to do and some of our challenges and why we turned to Apache Spark. And if there's any questions during this, please raise a hand or just yell. So the challenges our customers, and I think generally the ecosystem has, is you have pretty complex OLTP type systems that are doing a lot of different ETL all during the day, and they're wanting to do that more and more frequently. And when you get this data, you generally put it in some sort of operational data store, and then you spin off, data warehouses, things where people are running analytical queries, or you spin this off and you say, well, I'm going to run Spark or SAS or someone like that against it. This is becoming more and more expensive because each of these are separate environments that you're paying for, and each of the environments are closed off. And that's one of the things I'll talk about, what we've done with Splice Machine and Spark, being able to open it up to other tools and actually Spark to run against Splice Machine. So this is the challenge in the space. You have your transactional systems, ever more expensive operational data stores. Those need to be spun off into analytics. And this is really no longer an adequate approach. People are wanting to take in transactional data in real time, and they're wanting to run analytics against it. And as this community is focused on a lot of people, in some sense, building smart type applications with machine learning. So what you're seeing is, as the data gets larger and larger and is coming in at a quicker and quicker pace, this vision of being able to take the data and start moving it all over the place probably isn't realistic. So this is, kind of why is this what we're doing? Now at Splice, we originally said we're going to solve the RDBMS problem. And with our first release of the product, that was our focus. So everything from constraints, foreign keys, primary keys, all those core data management issues we tackled. But we fell in this problem. And the problem is very simple. You're wanting to do transactional processing or real-time processing of small events, and you're wanting to run analytical type processes, which are inherently, I call them destructive, but there are a lot of computations, a lot of memory usage, a lot of resource management challenges. And what happens is, and what has happened with traditional databases, is this completely bogs it down. So if you're trying to run analytics and some sort of real-time 5-10 millisecond delay sort of application against it, your transactional processing completely stops behind all of your large analytical processes that are running. And to be honest, we fell in that at Splice Machine after we did our first release. We found that, well, you could run a transactional system on it, and that would work well, and you can run analytics on it. But when we tried to do them together, that's where we really struggled. And our idea was, okay, you can just say, no, we're just going to be a transactional system, or no, we'll just focus on analytics. But at Splice, we realized that applications have components of both. They have both transactional requirements or real-time type requirements, and they also need to be able to support analytics. And I know I've seen use cases with Spark where people are trying to access data stores where data is changing frequently. So what we focused on was workload isolation at Splice Machine. Simply put, you have HBase for your transactional processing, which it's well equipped for. It's well equipped for single row lookups, things that are going to go against block caches and things like that. It's very much optimized for random reads. And then if you look at Spark, Spark is a great data flow engine for analytical processing. And that's the focus of that. So what we really tried to do is instead of saying we want a single engine architecture, we pulled this out and said, no, we're going to do a dual engine architecture at Splice Machine. And this is, I wanted to set the stage of like why we hit and some of the challenges we had, and then I'll go into some of the things that we did that I think are innovative and interesting for the community at large, whether you're using Splice or anything else. Yes?
So do you allow data manipulation through Spark, or that is only for data aggregation and reading?
It's a great question. So one of the key things for me, yes, the question is, do you allow data to be basically changed through Spark, or is it only done through HBase? And what we've done is whether you're on the transactional side, where you do single inserts and index updates and things of that nature, or if you do it through the Spark side with big batch and large movements, both things will write into HBase. And neither are second-class citizens, so they still do foreign key constraints, check constraints, triggers, everything. Those triggers can run actually in Spark when you're inserting data, like a large insert statement. I'll show some examples of that. So we wanted both to have the same characteristics. So when Spark is reading data, it reads it consistently. It does snapshot isolation, so it actually gets a consistent view of the data. So both can do that. Yes?
Do you access HBase directly, or are you using Phoenix?
We don't use Phoenix. And when we access HBase, and I've got a slide on that, if you don't mind, I'll talk about that, because I think that's one of the innovative things that we've done. Base. It was Java-based. It gave us ODBC, JDBC compliance. Then we built on top of Apache HBase and Hadoop. It has auto sharding, high availability, and it has a proven scalability of hundreds of petabytes. And then what we realized that we had to do was move to Apache Spark for our analytical engine. Before that, we had kind of wrote our own analytical engine, and it was a very simplistic analytical engine. Intermediate results would be written and replicated, where in Spark, you have lineage, so you can recompute those without having to write multiple copies. We didn't have all the sophistication that Spark had as a data flow engine. That's why it was appealing to us to embed it in our analytical processing. And I don't know how familiar, I wanted to do one quick slide on HBase. I don't know how familiar everybody is with HBase. HBase is an LSM tree architecture, so immutable files are flushed and written. The data is stored in sorted order. There's a mem store and a write-ahead log for durability. And this is how this is a kind of a classic, Cassandra is also an LSM tree, but it allows you to have really high write throughput. But there's a caveat, and that's what I'll talk about of how Spark solve that caveat for us. I wanted to show you this. This is how we just talk to Spark, about Spark to our customers. And this should be pretty straightforward. We talk about how data sets are broken into partitions and how that's working. So enough of this piece, but I really want to talk about, so how is Spark really making us work well? This is one of the things when you were talking about HBase. We had challenges with HBase. Specifically compactions. So if you search online, Google HBase compactions, you'll see 20,000 not very nice message board communications. People saying, oh my gosh, this slowed the system down. I don't know what happened. When you have large data movements in HBase, where you try to read large amounts of data, all kinds of problems if you're still trying to do transactional workloads there. Spark is helping us to do index creation, statistics collection, imports, monitoring imports, reporting to us when there's errors in imports. So we use accumulators in real time as we're loading data. They will actually show what record was invalid, so someone can look in the UI and see that. We use it as an admin UI, and I'll show you that. We've customized the Spark UI to be able to show query processing, which is extremely powerful for our users to actually see how data flows. We've done it for analytical processing, for pipelining the data. Lineage is the big thing over the data flow engine we had before, so we don't have to replicate intermediate results, which is really, really expensive. And lastly, we're starting to incorporate the machine learning libraries directly into the RDBMS for smart applications. Okay, so let's get to the technology piece of this. LSM tree, this is HBase, Cassandra, any of those sorts of things. And one of the things I noticed about Spark and the usage of Spark, very much to machine learning libraries. But one of the challenges, the Hadoop ecosystem and other key value store or transactional store databases, one of the challenges they have is you usually have a whole set of things that are transactional, quick range scans, things like that. But then you also have these kind of background processes like compaction or statistics gathering or things like that. And the database teams were working so fast, they bundled it all together. And that gets back to that problem of trying to do analytical and transactions in the same system. So this was what HBase looks like, and these spikes are when compaction is going on. So it's literally a heart attack to the transactional system. And this compaction runs in memory in HBase. It actually is loading massive files into the same JVM that you're using to serve block, doing really quick row lookups, block cache lookups, things that are supposed to be happening really quickly. Your system starts to have, garbage collection issues. Your system, then you start having I/O issues because you're reading from the same HDFS input stream, which blocks. So you start to have all these really significant issues. And what we thought is, okay, this is a unique opportunity for Spark and one we haven't seen, but I think it's extremely valuable. What if every time we want to run compaction in HBase, instead of running in that JVM and beating the heck out of HBase, what if it ran in Spark? It's Java code. We can pretty easily wrap that in a function and call it into Spark. We can customize the UI. There's some nice tooling for that to where we can display, hey, this compaction's running, and oh, by the way, when you see it running, you'll know what table or index is being compacted, how many files, how big the compaction is going on. So we went from a thing that was keeping HBase from being successful in my mind, and really it's the first thing people say is a kind of caution against HBase. But by using Spark and using it a little different, we all of a sudden now have something where you can monitor the compactions going on. You can resource manage those against queries that are going on and other things that are going on in the database. And you have, like I said, complete monitoring and isolation of this activity. And this, obviously we're talking about Splice, but if this was Cassandra, similar concept. It's an LSM tree. It's going to have to do compactions. Do you want to do that in heap in your JVM? So this is a use case that I think is very different than your normal Spark machine learning type use case. Now to your question on HBase. The big problem with HBase is that most people, what I say, they go through the front door to get the data for analytics. What does that mean? They open a scan to HBase, and they start reading from it. That's how Hive integrates with it generally in other products. And the knock against HBase is it's slow. Because what's happening is the HBase process is doing mostly a short circuit read from the Linux file system into memory in the Java process, and then you've got a remote scan from one Java process to another, and you're dumping a ton of data across that. That's an extremely inefficient way to transfer large amounts of data. And that's a huge problem, and that's where the perception of HBase is, hey, it's slow. At Splice, we said, okay, let's re-envision that, because that's not even going to be close to performant enough for us. So we said, look, why don't we go directly to the files, because they're immutable, right? And then we know that if somebody's actively writing to it, there'll be small deltas in the mem store of updates that are in flight. So what if we just go directly against the files via Spark? So it's doing a short circuit read from the Linux file system, native read, getting the data in. And the small deltas, we're going to go ahead and read from a remote scan. So instead of, if we're reading 100 gigs of data, instead of reading 100 gigs out of a Java process to another Java process via a remote scan, why don't we read 98 or 99.5 gigs from the file system directly into memory, and then we'll get that little small delta and merge that together. And that's where you get the performance that you need to actually be, in my mind, kind of coherent as far as the speed you need to get the data back. So it avoids the slower HBase API. It doesn't put load on HBase, because that would be bad as well. So when you're reading through HBase, you're not really, even if you have an analytical process reading from it, you're still causing a lot of, you're killing your block cache, you're creating objects there. That becomes problematic. And the other thing is, and what's neat about Spark is it still follows the map-reduce paradigm, the input-output formats. And if you go underneath there, there's still an output committer. And that's really important to us. So everything we do is transactional. So when we read, we have a transaction that we're reading as of. So if data's in flight, we'll ignore it. And changes we'll actually put together in a snapshot isolation system. And that's absolutely critical for us, because Spark was smart enough to use that structure. But the key thing for us is you're not sacrificing consistency, which is the strength of HBase. You're not sacrificing that. So if you're an application, the fact it's running in Spark, you're still going to see a consistent view of the data. If you just wrote it, you're going to get the data that you wrote back, even in an analytical query. Does that make sense to everybody? And I think that's actually an important thing as we look at even other storage layers. The question I always have is, okay, there's a front door for real time, but do you have a way to go directly to the file system in a coherent way to do analytical processing? And that's something I don't think we think about when we choose real-time systems. But I think it's absolutely critical, and something we'll have to kind of grok. Second thing that we did is, whether you're in the transactional system or the analytical system, we still do generate bytecode for your projections, things where you're comparing like your like type clauses, things of that, where you actually have bytecode where we're doing those comparisons. So we're still using an optimizer, and the optimizer does the plan, and the code, and that code, when we have it, is shared between HBase and Spark, because I can ship that bytecode over there, and then that's what's actually used to do the evaluations, like the projections and the filtering and things of that nature. I'm going to go through our architecture here. So for everybody, HBase, so it has its region servers. We're embedded in there. We're doing snapshot isolation, indexes, constraint checking, all of those sorts of things. And then co-resident on those servers, you have multiple executors. So in Splice Machine, we use Spark on Yarn. So as we need resources, it'll dynamically generate executors for us. And that's been really, really powerful for what we're doing. So as the analytical system needs more and more resources, we use Yarn to get that understanding of what capacities the cluster has. And then I'll go into how, even inside the analytical system, we have the resource management and kind of how we set up the resource management for Spark for our database. Okay, so how does this thing work? SQL comes over the wire, usually ODBC, JDBC. You optimize the query. So it's using statistics and statistic caches. So it's going to figure out, well, what is cardinality of the data? What are those estimates? It's going to push predicates. It's going to unroll nested subqueries. So if you're like a marketing app with a lot of nested subqueries, it's going to unroll those, make them joins. It's going to generate the optimal bytecode. So it's actually going to generate bytecode that represents the plan. And if that cost and the size of the data is small enough, it's on HBase. It's going to execute the OLTP query directly from the bytecode, doesn't serialize anything over, uses the block cache and Bloom filters to optimize data access. This is really for real-time and quick access. And it's going to return the results. Okay? But what if it's an analytical query? What if it's too large and I don't want to affect HBase? It's going to generate a Spark execution plan. So all of our SQL goes into, it's a result set basically that can, it explains itself. And fundamentally, every one of our result sets is an RDD. So anytime you have a SQL statement, I'm sorry, what? We use RDD right now for where we're at, yeah. Now we customize all the serialization between it. And what I mean by that is we're doing our own row serialization of the data. Because we have data coming back in bytes and we don't want to convert it to objects. So we have a whole host of optimizations about basically trying to keep things in bytes as long as possible. And if they need to be transferred, we never convert. If you're just moving data around, you don't want to take the bytes and turn it into a long and then convert it back to a byte. You just want to keep your bytes and ship them over the wire. So that's, yes?
Are you using data set, Spark 1.6 data set?
No, we came up with we call it a data set abstraction. And what we thought of there is, look, it's a data set. It's vague, and there's instructions I'm going to supply to it. But the key thing for us is whether it's real time or it's analytical, and those are, right now we have a Spark, and we have the side that runs in HBase. We have another data set abstraction for that. Regardless of whoever's doing that, we have those instruction sets to do that. So for us, we don't use the Spark data set, we use this concept of a data set, and we wrap everything around it so that we could use other data flow engines. If we say, hey, look, we want to use data frames, we would then create a data set for data frames. So we can have different implementations. That's really our focus, is to wrap around really, here are the relational algebra instructions that our database is going to be doing. And then different data flow engines can handle that, those instructions. That's our key abstraction. Does that make sense? Cool. Yes?
So when the query is executed through Spark, so at some point, does it touch the HBase engine to get the data from HBase files?
No, so it goes directly to HDFS. So when I say, hey, read the customer table, it'll go and it has an input format that points to that. And what's special about our input format is instead of going to HBase to do a remote scan, it'll say, okay, here are the files for that region, and then I'm going to do deltas with the mem store for that region. And then it has its own splitting. It uses the indexing of the H files to generate cut points and blocks so that we have, we don't have regions of different sizes being computed at different timings. But it goes directly against the file system. And then we have concurrency guarantees while we're running that. So if somebody does a compaction, the files are fundamentally changing. We do compare and swap operations there to make sure that we don't get caught reading files that disappear on us, right? Or a split. We make sure that we don't get caught in those sorts of situations.
So if a table is being updated through HBase,
Yes.
as well as through Spark, the same table, how do you handle that?
Exactly. So remember, it's an LSM tree. So all of our data is written into HBase. And what you have is it's immutable. So you're just writing files. And then when we write data, we guarantee transactional integrity. So if multiple people are writing the same record, there's different isolation levels that will throw up basically different exceptions based on your writing of data at the same time. So the writing goes through HBase, because HBase is the way that you're actually figuring out who's writing, what transactionality is happening. And then when you read, you're reading directly from the file system, the HBase files, and doing a delta with the mem store. Hopefully that makes sense. So really what we're trying to do is keep HBase from destroying the block cache when we read a lot of data, and we're trying to take that load off of HBase, which it just doesn't do well. And that's kind of been proven out. I mean, a Google search will kind of show you that that's not the way you want to access HBase.
What kind of input format are you using to read the HFile? Is it HFile input format, or is it?
No, we wrote our own. So it actually opens an HBase region. So HBase has utilities to open regions that just go directly to the files. And then we use just a memstore only scan from the region. And we merge those two together. And we have concurrency guarantees on the server side when we make that connection. Because you have to, like I said, don't get caught with the files moving on you. Make sure that your scans don't time out, all these sorts of things that you have to, kind of the nuts and the nitty gritty stuff of it.
Part of this stuff open source?
We have not open sourced that, no. A lot of it, though, to be fair, you need a transactional system to make it, in my mind, coherent. Because you're really starting to say, if I see data in flight, you just ignore it because it hasn't been committed, depending on your isolation level. So it's really, I think the concept of this is really driven by you have to have some sort of transactional nature to make it, in my mind, coherent.
So is it okay to say anytime a write operation takes place, whether it is through HBase or through Spark, it goes through HBase?
It does go through HBase for the writes, correct. And we have our own write pipeline that we've built that's specific for HBase, where we have non-blocking writes. So when we stream data from the thread, we break out parallel write pipelines, and we even piggyback writes onto region servers, not just regions. So we're starting to tackle the mini node problem where you're doing a lot of RPCs. We start to piggyback, cut down the number of RPCs, and we'll batch in rows of like 20,000. So instead of doing a write-ahead log for every entry, we do 20,000 and put that in a single write-ahead log. And HBase is much more amenable to that. So we can do 100,000 writes per second per node, where HBase generally can't get that, but what we're doing is we're batching that up and we're making it less disruptive for HBase, if that makes sense. So we submit the Spark plan with the bytecode. And when that happens, the fair scheduling piece of Spark kicks in. But most importantly, we go through Yarn. So as a group, we made a commitment that we would use Yarn. So even our developers, we use little Yarn consoles, and that's how we run Spark. Because we really feel like you have to do it in some sort of resource management framework, and you can't step all over what else is going on in a Hadoop cluster or environment. So that's something, that was just a decision we made. We think there's things that we don't like about Yarn, of course, and all those different things, but in general, that is our strategy for dealing with the classic. I've got a lot of things running, a lot of people competing for the same resources.
So when we execute a query on a Splice machine,
Yep.
what factors determine whether it should go to a Spark engine or to HBase?
Yeah, it's a great question. So we have statistics. So that means we know cardinality, size of the data, what number of distinct values, null values, those sorts of things. So based on that plan, you have an approximation of the number of rows. If there are no statistics, which is classic in databases, right? Nobody runs statistics, and it's kind of, I don't know what's going on. HBase is special because the region servers keep track of the store files, the size of those store files, and you can make a reasonable approximation that I'm going to look at 100 megs of data. Do I want to look at 100 megs of data in HBase? Probably not the right way to go about it. But do I want to look at that in Spark? That seems probably reasonable. So we do those approximations based on the plan. But it'll look at the statistics. If they're not there, it'll use a heuristics model. But it's pretty accurate because it's using the store files. And remember, the store files have an index. So it knows the blocks and the row keys. So you can get a pretty good approximation of at least the amount of data you're going to be scanning. So you know whether this is going to be 5 rows or 1 million rows. It's relatively advanced, I think, in that. I'm sorry. Yep. No.
Where do you keep your statistics and your metadata?
It's in HBase as well. So we have a dictionary tables. So when Splice starts up, we create, gosh, I don't know, 25, 30 tables. And they're managed transactionally, just like the other tables. So when you create statistics, they're written in that table. And I think the hardest problem we've had is the classic distributed computing problem of, you think about metadata and statistics, it's extremely hard when you have a multi-node environment. That stuff has to be on cache, basically, on every one of those nodes. And then the challenge happens is when you update it, you got to do some sort of two-phase commit sort of protocol to eject the cache, understand that your ongoing DDL transaction going on, and be able to clean that out in a transactionally reliable way. That's been given, that's a fit for us. That's something that we've worked on over and over to get it right. That was, no, we don't, not internally, because we need something that's extremely fast. Like I've got to use, in the case of like a prepared statement, I've already got the bytecode done. I'm back immediately. So it's not a low latency, or it's not like a high latency type environment. It's really low latency. Yeah, no problem. Sorry, yes.
So we have a different, when you're speaking about, you're trying to merge OLTP and OLAP, but actually OLTP is O-based and OLAP is actually columnar-based.
Mm-hmm.
And if I'm going to compare columnar-based, like I'm going to put the file in Parquet, I will be able to, and usually analytics are going to look at a specific column.
Sure.
You won't be able to get that kind of performance from OLTP because you actually have to scan all the rows which are actually going to be involved in the queries.
Okay, so
yeah.
no, this is a good question because I spent a lot of time thinking through this. So you are right. So most OLTP systems are row-based. However, those systems do have some analytical operations. Even creating an index in those systems, in essence, is an analytical type operation. You're reading a lot of data in. So I think there's a need there just for the transactional piece of the system. I think in operational data store use cases, where you're doing a lot of the business logic of organizations, where you're doing triggers, where you're doing workflows, data management, that's still really critical. I agree, if you remember the diagram I had, where you had the transactional system going to the ODS, and then you get these optimized columnar stores for read-only, a read-only store. I still think that's absolutely critical, and I agree with you. I think, to me, it's not even so much more columnar, it's really about being CPU efficient, and columnar is CPU efficient. So I totally agree with you on that. I think the system, if we look at a system maybe 2 or 3 years from now, what I'm showing you, you'll have what's going on on the HBase side, and then those regions will have dual representations. That's what Google has. They have a write optimized store right next to a read optimized store. So you can imagine as we run this compaction, I could easily generate, in your case, a Parquet file, right next to it for the analytical to be even faster. That's not a reach, conceptually for anybody. But I do agree with you, but the key thing is, from my perspective, applications modify and change data. And our goal at Splice is about computing the uncomputable. And I always laugh because uncomputable is not even a word. But our focus is, well, think about that. The challenge, the data that people don't access and they can't analyze and can't do machine learning on is the data that's rapidly changing. And that's the data that's in flux. That's the data that's actually interesting if you're in a hospital or anything else environment. That's the data that is absolutely critical. So that's kind of our passion versus the read-only optimized store. I think there's a lot of people solving that problem for read-only analytics.
Trying to do Lambda.
What's up?
Trying to attack it using Lambda architecture.
Yeah, so if you look at what we're doing, it is kind of a Lambda architecture. I'm reading the store files and doing that piece. The challenge with the Lambda architecture is it's really for doing really quick analytics in real time. And it works in some, it's very much like a heavy, in my mind, a heavy developer approach to getting those analytic numbers more and more accurate, right? You have the background process that's getting it close, and then you merge in your weightings and everything to come with that ultimate aggregation. I think that's going to become more and more important, but I think with Spark, and you start to use caching and other concepts, you can start to build things like materialized views and things that are more Lambda-esque. I think that can become a reality. We're not there at Splice Machine yet, just to be honest, but I see those things in the future for a lot of people. So the big thing for us is we do generate that RDD from the H files and memstore and HBase when we're wanting to scan the data, and we execute query and return the results. sounds like crazy bytecode and everything, but if you actually looked at the code, it's very similar to all the other things. It's map, you have your functions, your flat maps, all the different functions and relational algebra you're applying. So all of our operations, relational operations, have a set of instructions that if you looked at them, you'd say, hey, I recognize that. Yeah, it might be a little different how we do a projection under the covers, but you would recognize it and say, oh, I get that. So that's what we're doing under the covers. The key thing for us is now these two processes are completely isolated. So they can have different nice scores, CPU prioritization. These things are isolated from each other. And that's the trick of a transactional system. Get all the analytical processing off of there. What we use heavily is resource management in Spark. Because it's nice to say you have OLTP and OLAP, but that's not actually how it works, right? Because inside OLAP, you have import statements. How should they be prioritized? And how should the scheduling algorithm pick those tasks to run? What about compaction, right? What about a query? What about an administrative process like running statistics? How should you weight statistics running versus an import? Which one's more important? And we allow our customers to change this, but by doing this, all of a sudden you have a system where you can start impacting the behavior of it. And you're doing it inside Yarn, where you're not overwhelming the cluster. You can go where there's an existing infrastructure and create a process that functions. This is extremely, I've been really impressed with this piece of the software.
So the magic to all this, I see, is that your DBMS is written on HBase, and as a result, Spark can just get to it through Yarn and all this concurrently.
It does, but the key thing we did is we said we didn't run and kind of act like there weren't problems with HBase. And I think I'm saying HBase could be Cassandra, whatever your key value store is. The question is, can you make your key value store behave with Spark and do it in a way where you're not basically creating more problems than it's worth?
Yeah, most traditional RDBMS is not HBase. I mean, they're not columnar stores, so
right.
we had this integration problem.
Yeah, it's a big challenge, but it's something we focused on. So this allows people to change their resource pools, which we thought was extremely compelling. And the thing that was really exciting for me is, I don't know how many people have used the Spark UI, but you can customize that in amazing ways. We actually put in all of our SQL into the UI. So when you run a query, you see your SQL there, you see your tasks that are executed. So each SQL statement is basically a job. And all the instructions for that SQL statement, even subqueries, procedures, all these bizarre things that are going on, it's just basically a Spark job. It gives us monitoring, eventing. This is a TPCH query with unrolling, right? So this starts to get pretty interesting. And you start to see, well, these things are executing in parallel, and you can see where your dependencies are, what is running, how many tasks, and then all the monitoring of Spark becomes a whole lot more interesting. Now you have a database where you see what tasks are running, what their splits are, how much data is going through. All of that data is coming in, and it's coming in real time as it's executing. Before in Splice Machine, we had a real problem. We thought we had really cool technology, said, oh, it's running, see how fast it runs, great, but no one could actually visualize the internals of the database. What's actually going on? Has this finished? Well, how much data did this read? How many megabytes? How much did it shuffle? How much did it move across the network? I can look maybe in Cloudera Manager or Embari or someplace and see data going across the network, but I can never trace it back to the actual query. What the heck's going on? And I thought this was one of the, so you can actually see, like I said, the visualization stage of merge sort joins, table scans, projections going on, how many rows are going through that. And then when you actually go into a stage, in the stage we implemented accumulators, so you can see the number of rows as they complete that go through. For imports, we have accumulators that show you the rows that failed. So when you're importing data and you're starting to see a few rejections, you can actually go in the UI and be like, oh, there's a comma there that's misplaced, or that's got 2 double quotes. Duh, that's a bad record. You can actually see that in real time, which I think is amazing through this UI. Has anybody customized their Spark UI at all? No? I mean, I was amazed by what you can literally put whatever you'd like in there. We put the entire, basically, explain plan information in there so that you can actually see how many rows we expected. You can see that there's a difference between we expected 100,000 rows and you returned 200,000.
How do you feel about customizing the dashboard? Is it down to modifying the source code, or is
No,
it
you just,
annotating your job?
yeah,
somehow?
there's like job groups, but you can directly, there was a blog post on this, and I can even post some of the code afterwards if people are interested, but you can actually set all of these fields directly on it. It's a little hook that someone built in. The Spark SQL guys actually built this hook in because they were trying to do, I think, a similar concept, and you can hook it directly in. So you can put whatever information you would really like there that were maybe used to make the decision, but it's extremely powerful because then the process that you're doing is actually in your language, which I thought was really critical for us. The cool thing, relational databases in general don't like to read files from the file system because that's a very expensive memory problem. Now we have virtual tables. So we can use Spark that can already read text files and CSV files from the file system. And we use our system to dynamically type those into different, this is a varchar, this is, and you define that. And now all of a sudden I have a relational database that can do joins with files in the file system. Can join with a web service. You start to get this nice open architecture that you can implement your own virtual table interfaces. So this is something that was really important to us, so you can start querying data directly from S3. You import data, you can just run the query against it. We wouldn't have been able to do that without Spark. This would have been not possible for us because we wouldn't have felt comfortable saying, in our HBase memory space, we're just going to start loading random files in there. That would be too dangerous for the performance of HBase. Yeah.
Also there, from a Splice Machine, you can connect to Oracle and DB2 using
Yeah, because it's just a JDBC. We have a JDBC VTI, so you can connect via JDBC and actually execute a SQL query in Oracle and get the result set. And the result set will be dynamically typed based on your query by our parser. So even cooler, when you start joining the data back, you execute your SQL, but we're already converting it. That's a varchar in Oracle, it's a varchar here, and we're doing joins based on typing.
Can I just select from Oracle and insert into Splice
Yes.
Machine in one statement?
Yes. That's what I think the power of this VTA, because for us it was having more of an open architecture of getting data quickly from different systems. Yes?
Can you actually write a single statement and have it deal with different sources?
Yes.
One from Oracle and one from...
Correct, yeah. And then the VTI has an implementation of cost. So you can implement that however you want. So for us, for example, on like flat files, we do an approximation technique based on what columns you gave us and how big the data is. And that's kind of our technique so that we know, hey, that right side is actually 1 billion rows and that left side's 20. Maybe do a broadcast join to the right side. That's how we go about doing that. And the last part, and the part that was kind of cool to me is, since our result sets are, in essence, instructions for Spark, you can slap together a quick stored procedure, pass in whatever SQL statement you want, and the results of that statement, it'll run multivariate statistics on it. And you're not running the SQL in the database, and then the analytical engine's running on it afterwards. It's just a set of instructions. And it's just thrown over to Spark, and it's doing the SQL. It's just a big, long processing chain. And it's doing the statistical analysis and returning it via SQL to you. So this is an example of all of a sudden, here's a procedure that does some pretty advanced multivariate statistics that is pretty simplistic to put out there. And you can imagine linear regression. You can imagine different classification algorithms. It's going to be extremely powerful for people to be able to do that. All right. That's all I had. I just wanted to share with you guys kind of some of the things that we did. And just to kind of go through those again. Key value store in your storage. Never underestimate Spark's ability to make those systems more efficient. That was one thing we learned. Second, if you're going against a real-time type system that's changing, I would always suggest to think is there a way to go directly against the files versus going through a remote call? That's really expensive. And really spend your time trying to come up with an input format that's very efficient for doing that. I would heavily suggest modifying the UI. That's so powerful to see whatever it is you're doing in the language that you're doing it. I think that's one of the more powerful things that we've learned from Spark. And I think the UI is tremendous to be able to see kind of what's going on. And with that, I'll open it up to questions or concerns or anything.
Do you
Yeah.
publish your meta schema so we can get to the data? I mean the schema information.
Yeah, so it's a normal data dictionary. So any JDBC or ODBC client, it can say, get me the schemas, give me the catalogs, give me the tables, primary keys. It follows all of that model. Yeah. And that's how you can do, ERD diagrams, all the things that databases do for you. That's kind of one of the things. So you can plug in any SQL tool to it, and it will already show you like the foreign keys and draw that stuff for you. Yes.
John, thanks for the great explanation.
I hope so.
So I like so you mentioned basically we have this data set abstractions, right? And so can you imagine, plugging in Flink instead of Spark and abstract, the memory computing engine as well?
I think Monty would probably kill me if I start trying to throw it on. No, I mean, you see that. I think for me, it's, are people comfortable with it? We have partners that are running the Hadoop clusters, your Hortonworks, Cloudera, MapRs, and you want to make sure it's supported. You want to make sure that no one's going completely off-road to where, you get into a bad situation. So for me, it's all about, is it supported? Yes. Are people excited about Flink? I don't know. I mean, we've kind of kept track of Flink at Splice. I'll be open about that. It's on our radar, but right now it's Spark. And we're really just, to be honest, we're just cranking and making sure we can do all the RDBMS capabilities and execute on this. I mean, this is I think a very audacious goal of what we're doing. And I'm excited where we're at with this 2.0 product. And I want to just stay focused on our customers before going to Flink or any other thing.
But in terms of abstractions, are you capable, right?
Oh yeah, we're capable, and we've even started to abstract away the data piece as well, so we could use other storage mechanisms. But we're pretty focused. Scarily. Yep. Yes. It's different. So we run on the 3 different platforms, and then we have different versions of Spark on their releases. So it's usually like somebody will say, like, I'm running on Cloudera 5.4.1, and we have a build of Cloudera 5.4.1, which has a version of Spark that's appropriate for 5.4.1. So we really try to make sure that, because in essence, we're on somebody else's architecture in the sense that somebody may have Cloudera on 50 nodes or MapR on 50 nodes, and we have to be able to come into that environment, behave, run in their resource management framework, and do all of that. So we're very tightly integrated with those releases. Yes?
For the Spark OLAP related stuff, what kind of actual time ranges are you typically targeting in order to achieve? Are you looking at things like OLAP queries that are running on the order of like hours, minutes, seconds, or milliseconds?
Good question. So we target anything that's over probably about half a second. So our delay is about 200 milliseconds for the instructions to get around. So anything over that, then it becomes coherent to do. Does that give you a kind of ballpark? That's kind of where we're, so you think you have a 200 millisecond delay on the, just getting things scheduled in Spark and everything going. So that's kind of where we're at right now. That keeps getting less and less, but that's where we're at right now with 2.0. Yes? Does it support multi-tenancy? The Splice Machine database, so you can run, a lot of that is, to be honest, the harder part is trying to figure out how you do the yarn thing, and then try to figure out like how are you going to do the resource pools to different places. Right now, we have that where it works for kind of, we've got it pretty structured about you can change the priorities and stuff. We're going to build an interface to that so that based on your connection URL and what you supply, then people can write an interface that would say, okay, the connection URL was this company, like say you're a SaaS provider, those will go to a different resource pool in Spark, thus you can keep track of the resources and weigh them against each other. But we haven't got that far yet as far as, yeah, you can see how we're going to do it, but we're really, like I said, pretty maniacally focused on just making sure that every feature in a relational database, if you have 15 levels deep of triggers, those all work transactionally correct. I mean, we're really focused on that because that's how people get confidence in your database. Yes?
Maybe this is an orthogonal question to what you're focusing on, but I was just trying to look at the NoSQL world, where there's the concept of flexible schema, right?
Correct.
Are you in any way trying to address that shortcoming in relational database?
Well, it's not a shortcoming in our database. So let's just talk about this directly. You have 10 columns, right? And how do you handle that? You have your 10 columns there. And if you want to add a column, you have an 11th column. And we already know how to handle this, right? We all know protocol buffers. And what is the approach of like a protocol buffer and Avro? You just increment at the end, right? And if you see data that you can't understand, you ignore it. And we're very similar. So when we have our data and you want to add more data, that's fine. And you just keep adding columns. And if you drop a column, that's just a logical, hey, position 9 is no longer valid in that data set. And you just ignore that when you're reading and reassembling the row. So you can have a completely flexible schema. And you don't have to, like an alter table in our system on our 2.0 product, that's like a few millisecond operation. All you're just updating is dictionary. You don't have to physically go in and change the data. If you're saying, look, I'm going to drop a column, we don't really drop a column. You tell somebody who's reading the data, ignore that column, in essence, from the dictionary. Likewise, when you add a column, all you're doing is saying, it's null now, but it may be populated in the future. And as you populate it, you populate it and you do your LSM merge and put that data back together.
No, it sounds like, you're still doing the alter table operations, right? So
Yes. It's still typed. The system is still fundamentally typed,
right,
yes.
so that's my question. So in a lot of the enterprise situations, there are different people handling different segments of a database. So for example, somebody has to give a request to a DBA to do the alter table operation. So that takes a lot of time. So they don't want to go through that process. So they want the applications to handle all of this, and that's why they say NoSQL is the flexible schema is a advantages of this. So that's what I was trying to get at.
Yeah, no, I don't disagree that maybe storing in JSON is a great approach. There's obviously challenges, right? You can't apply constraints. It's a really poor storage format. It's really I/O inefficient. So there are other challenges there of being able to do it. So I think you have to weigh those two against each other. Yeah, but I think that's fair. Yes, sir.
Can you consider the scenario where I want to query Splice Machine from Spark?
Yes. So when you do it, you just supply the SQL and we'll return the instructions. And then it's lazily evaluated. So the fact that all of our result sets, we can return the bytecode to Spark. So if you're in a Scala client, you can return that bytecode and then they can actually execute it directly there. Because there's no, the hard part for me conceptually when I was doing this is there's no Splice or Spark. All of our instructions are in, we're sending to Spark. They are completely contained and can execute themselves because they have all the data they need to be able to do that. So even if you're inside Spark and you're querying it, all you have to say is, this is the SQL I want, return that bytecode instructions. Those bytecode instructions can regenerate an RDD, which is a result set. And that's what I was showing in the procedure, is that basically the instructions is this result set. So before you iterate on it, that can just be converted directly, and I probably did a poor job of that, but it can be converted right to an RDD. And then we provide utilities to take those typed, like varchars and everything, and most of the machine learning is vectors. So we already have conversions from int, double, stuff like that to vectors so that you can perform, in essence, machine learning. So the key thing is our instructions for that SQL are basically an RDD. And it's similar to Spark SQL. They do a similar thing where their SQL is actually then instructions. So it's not like I picked this out of thin air, but it's extremely powerful because you're no longer executing your relational database then doing analytics. It's just a set of instructions that you execute.
You can
Yes.
use Toad-like tool to interface with.
Yes, JDBC, ODBC, any of those types of tools. Yep. Yes.
So you mentioned protobufs and Avro. Are you
Yeah.
using one
Yeah,
of
so,
these?
so HBase is using protocol buffers under the covers. We use it for message passing. So if messages change or anything has to be persisted, you can do that without, obviously having serialization breakage and rolling upgrades and all that stuff. So yes, we use protocol buffers, just to be open. We don't use Avro. At least I don't. I'm sure there's some product that's bundled in some large jar somewhere it's using it, but we don't use it. Yeah. Yes.
So essentially, your query plan is a transformation of RDB. It's
Yeah.
a sequence of transformation of RDB.
Yeah. Yeah.
Question here. So you have acidity, so you have commits.
Mhm.
How does this scalable if your write throughput increases? How do you parallelize commits if you have to bring them all together?
So we don't. So that's one of those things. When you think about a transactional system, a lot of times people think that you keep it all in memory, and then you just write it on commit, right? But we're an optimistic system, so we're actually writing it in, and then when we commit, we then resolve and understand whether that data is committed or not. So if you're going to write 1 billion records in, let's say, 10 regions in HBase, you'll have sub-transactions that are writing into each of those regions in HBase that can retry and do small pockets, and they'll write in, and the data's going in. If you're trying to read, you'll ignore it because you know that data's in flight. Because when you try to resolve it, you say, hey, this transaction's it's not committed. I mean, and I'm at an isolation level that ignores that. And then when you say commit, and our transactional table is spread across the cluster in HBase, because HBase has row level atomicity. So once it is committed, it's committed in one place, it's completely atomic. So once that commit happens, everybody can resolve to a point in time. So that's our kind of what we focus on, is making sure that we have those, in essence, ACID properties.
My question was more of like, what happens if 1 million people write one row each?
Uh-huh.
How do you resolve that without bringing them all into? How do you scale that up?
Yeah, so let's say you have 1 million people that write one row each. They're going to get a transactional timestamp, an increment. So they grab their transactional timestamp and they're going to write it, which doesn't really have any contention except write a head log with its other peers. You're going to write that data, and then when you commit, you're going to write it again to HBase. So all of our transactions are actually persisted in HBase, the state of them. Does that answer your question?
Okay, take it off.
Okay,
Thank you.
fair. Any other questions? Thanks. I really appreciate this.
Guys, thanks for everything. Excellent talk.